So hello, good morning, good afternoon, good evening, everybody, wherever it might be. So now I return the favor. At the end of the previous semester, it was Tomek who introduced me, so now I introduce him. My revenge is sweet. So it is my pleasure to introduce TOMASZ MASZCZYK from the University of Warsaw, who will tell us everything and more about Hochschild cohomology for abstract convexity and Shannon entropy. Tomek, the Zoom is yours. Take it away.
Thank you, Piotr. Today, I'm going to speak about things which are apparently very loosely related. I'm going to mix things, and I hope that my mixing will be tasteful for you. So the title is Hochschild cohomology for abstract convexity and Shannon entropy. And I'm going to start with generalized third Hilbert's problem. If you think about a convex polytope, you can cut it using scissors in such a way that you can rearrange these pieces, and you can obtain another polytope. And the question is whether such two results of such dissection can be obtained without any restriction. So David Hilbert asked this question: are all convex polytopes of the same dimension and volume scissors equivalent? And after some time, people realized that it is not always possible. For instance, if we dissect such a polytope in such a way that we dissect lengths of edges and angles, then some strange combination of these lengths and these angles cannot be changed. This combined formal combination of sums of lengths and sums of angles was introduced by Max Den. And today, this abstraction for this equivalence is called Den-X variant. If you think about such formal tensor products like indent invariant, you should evoke the following construction introduced by John Milnor, who proposed an invariant of a field F, and it turned out that this invariant is a part of algebraic K-theory of fields, which after Matsumoto has very simple presentation as a quotient of the tensor product of tensor squared of invertible group of elements in the field F divided by relations. And around these relations will revolve all my talk, in fact. These relations are closely related to some special functions. And there are two kinds of functions in this story. One class of functions are called polylogarithms, and their infinitesimal counterparts. And this scissor equivalence problem can be rephrased in terms of some group, which is called the scissors group. And this infinitesimal counterpart of the scissor group is related to an infinitesimal part of polylogarithms after Categorical. It turned out that the condition of Categorical of being well defined with respect to relations of the scissor group, this condition could be rephrased as a fundamental equation of information theory. And the solution to this equation leads to Shannon entropy. So you see that information theory is closely related to algebraic K-theory of fields. I want to introduce something new in this story, namely, I want to connect this story with some approach of John von Neumann to convex geometry. He realized that if we define for two elements of a convex set, x and y, a convex combination with weights 1 minus 1 and 1 minus t, sorry, and t, where t belongs to the unit interval, then this operation satisfies nice algebraic properties. And I'm going to explore these properties. To such structure, introduced by John von Neumann, I'm going to attach some kind of Hochschild cohomology. And this Hochschild cohomology is an invention of Gerhard Hochschild, which was devised for constructing invariants of associative algebras. It turns out that thanks to identities of von Neumann, we can construct a very similar gadget for abstract convex sets. So let me start from polylogarithms. So we are fixing the field f of characteristic 0. By P1 of f, we will denote the set of f rational points of the projective line. And by symbols like Rn or R twisted by n, we will understand some obvious generalization of a real and imaginary part and real line or real line twisted by some power of square root of -1, depending on parity of this exponent n of this twist. Next, I'm going to introduce the notion of special functions, which are called by many names. They were introduced by Bloch, they were used by Bloch, Wigner, Ramakrishnan, Zagier, and Wojtkowiak, and they are called modified nth polylogarithms. So in this polylogarism, you have usual integral logarithm function combined with logarithms and Bernoulli numbers and factorials and powers of 2. Okay. So such a function, provided the absolute value of the complex number z is smaller than 1, extends as a function from C to twisted real line. Together with these polylogarithms, one could consider also their infinitesimal version after Catolino, who computed partial derivatives of these functions dn, depending on z as well as its conjugate. And there's a formula which expresses the differential of this polylogarithmic function in terms of some sums containing logarithms and polylogarithmic functions. Okay. How these polylogarithms are related with scissor group. So let's introduce the notion f with a double bullet, which is doubly punctured line, or f, the set of f rational points of an affine line. you can think about this as a triply punctured projective line when 0, 1, and infinity are excluded.
Tomek, so it can be the empty set in particular, right?
No, because F is of a characteristic 0.
Ah,
It's an infinite field.
okay, sorry. Yeah, somehow you didn't write it.
So you can think that F is an...
So F is of characteristic 0, okay. Mm-hmm.
Yeah. Usually F is a subfield of a field of complex numbers. This could be real numbers or some other subfields of C. So Caesar's congruence group is defined as a quotient of the formal integer linear combinations of these points of this F doubly punctured by the subgroup generated by the following relations. So these relations are built with symbols, square brackets around some elements of the field. Their fractions, their inverses and differences of 1 minus some element of this field. Okay, and whenever such an expression makes sense, it defines a relation in this free abelian group. And this is an interesting fact that this definition is fairly trivial, almost trivial. It's very simple and abstract. However, after Abel, we know that these identities appear in a very natural way when we start studying the dialogue function, for instance. Okay, and as a result of this appearance of these identities in the dialogarith function, we have a corollary that if we have a subfield of complex numbers, then the dilogarithm d2 is a function which is well defined on this quotient group, on this Caesar's congruence group. Okay, it turns out that this construction is very closely related to construction of some distinguished elements of algebraic K-theory fields. By Suslin definition, we can relate this construction to the congruence. We can relate this Caesar congruence group of F with the second Milnor K-theory. Okay, we have 4 terms in this exact sequence, and in the middle we have a map lambda. Okay, and this lambda is defined as forming a formal tensor power product of an element A and 1 minus A. Okay? And it goes from this Caesar's congruence group to the alternation of the second power, tensor power of the group of invertible elements in the field F. Okay, and next, the co-kernel of this is the Milnor group, and the kernel is a very important group, which is called the block group. Okay, and there's a remark that if you are interested in higher K-theory, then this block group, after rationalizations, is isomorphic with this K3. So morally speaking, in this exact sequence, we have kernel and the co-kernel, which are closely related to K-theory. Okay? So to understand what is going on, Goncharov devised a special higher analogs of this situation, some intermediate polylogarithmic groups, which are quotients of these formal linear combinations of f rational points of the projective line, divided by some system of relations. And these relations extend relations on the level of K2. And again, we have this second exterior power over Z of this group of invertible elements of the field F divided by 2 torsion. And we have a map, delta 2. For n greater than 2, we can construct similar analogs of this map. And we can define a quotient group, Bn after Bn of F. It is a quotient of the kernel of these deltas on the subgroups of relations Rn. And Zagier conjectured that these quotient groups, after rationalizations, coincide with the odd K-theory, algebraic K-theory of the field F. If this is true, it would allow to express the values of the Dedekind zeta functions, which are very important in algebraic in arithmetics of number fields, in terms of values of polylogarithmic functions. And these can be used to compute the values of these Dedekind zeta functions at integers greater than 1, as expressed in terms of values of these polylogarithmic functions. And for n equal to 3, such expected expression was proven by Goncharov. Okay, so this was the story about these polylogarithmic functions. And now we are going to speak about this infinitesimal analog of this. So instead of dividing a free group generated by this doubly punctured field, we take combinations of these elements of F doubly punctured with coefficients in the field F itself. Okay, and then we can divide it by some subgroup, which is defined as a kernel of some map. So we can associate with every element, class of an element A, a combination in the product, tensor product, of 2 different kinds of subsets of F. So the second factor is as it was in, for instance, in Matsumoto construction of the K2 of Milnor, but the first factorand is the additive group of the field F, which is the vector space over F. Okay, and then we can form a similar quotient, analogical quotient. This is equipped with some deltas, maps, which are analogous to previous deltas. And then we have a proposition due to Catolino, proved in '96, that for n greater or equal to 2, we have a morphism of real vector spaces. If we take the differential of this polylogarithmic function, and we do some enhancement to this, this will give us the function from complex combinations, linear combinations of doubly punctured complex line, taking values in twisted real numbers. And this is restricted to the subgroup Rn of C, gives us 0, which means that it factors through the quotient and gives us a morphism from this infinitesimal counterpart of this Caesar congruence group beta n of complex numbers to the twisted line. Okay. With this construction, we can associate another group, the Gothic B2, which somehow should evoke this Caesar congruence group, which is defined as a vector space over this field generated by symbols A in triangular brackets, where A goes through all doubly punctured field, subject to the following relation. Okay, and then it turns out that this relation is precisely this relation which is needed to obtain the isomorphism between this infinitesimal counterpart of the congruence Caesar group and this beta 2, another infinitesimal counterpart of previously defined P2 group. Okay, and they are isomorphic. Moreover, if we restrict the differential of this dilogarithm D2 to real numbers, then up to a constant factor, there is only one continuous function G, which satisfies such an equation, which is related to the previous equation. Okay. On the run of the proof of this proposition of Elbaz-Vincent and Gang, we will discover something very interesting. Namely, after changing variables in this function, one can translate this equation into some other equation in this bold red frame, which is very well known to people, especially to people working in probability theory or in statistics. Okay, this is a functional equation whose only up to a constant factor solution, continuous solution, is the following combination of logarithms and linear functions. Okay. This equation is known as the fundamental equation of information theory, and restricted to the interval 0, 1, has its unique continuous or even measurable solution, which is called the binary Shannon entropy. Okay. Moreover, this property could be this property of satisfying this functional equation could be used to prove, or could be used to generate more general expression, which is called the Shannon entropy, which is a combination. It's a function of coefficients of convex combinations P0 to Pn, which could be regarded as barycentric coordinates on a standard simplex. And many things were classically known about this function. However, appearance of this function in this context is quite unexpected. So people tried to understand the real origin of this function. And we have the following results. In 1956, Faddeev proved the characterization of this function in terms of several properties which should satisfy this function as a function of these numbers of the barycentric coordinates of the simplex. It must be invariant under bijections, it must be continuous, and for any probability measure, it must satisfy the following equation. Okay. So this is a very nice characterization. However, it's still not clear what is the reason why these properties are important, and what they can say about the real origin of this function. Okay, so more ambitious approach is a categorical approach when this entropy arises as some very natural construction on the category of finite probability measures. Definition is following. If we have the category of objects which are pairs consisting of a finite set X and a probability measure P, then we can consider morphism between such objects, and by assumption, all this morphism must satisfy measure, counting measure on these finite sets, which means that the following formula must hold. So jth component of this probability distribution Q must be the sum over all preimages of this J of corresponding probabilities in the domain of this map, of this morphism F. Okay. And then we have the following theorem. Assuming that we have a function mapping morphisms in this category to the half line from 0 to infinity, obeying the following very natural assumptions, which are called factoriality, which means that the composition of morphisms goes to the sum of these functions whenever these morphisms are composable. This satisfies convex linearity, which means that if we have the disjoint union of spaces, and we are taking the convex combination of morphisms, then the convex linearity property number 2 is satisfied for every convex combination, depending on the lambda from the interval from 0 to 1. And finally, it must be continuous. Then there exists a constant, positive constant, non-negative constant, such that for any morphism, this value of this function applied to this morphism F is up to this constant simply the difference of Shannon entropies. Okay, and this condition, these three conditions determine these differences of Shannon entropy uniquely, in a sense. So this means that we have very fundamental understanding, maybe not of Shannon entropy itself, but differences of entropies when we try to relate these entropies to some categorical construction. Okay. Understanding entropy is important not only for finite probability spaces. In 2012, Gromov started creating some program entitled "In a Search for a Structure," whose first part was about entropy. And in this program, he mixes geometric measure theory and tries to find formalism which would make the Bernoulli shift on homogeneous spaces functorial, which would be a rigorous mathematical foundation for physical ideas of Boltzmann and Gibbs. What are important mathematical features of these notions? So first of all, it is two categorical and asymptotic perspective. So as you remember from this categorical characterization of entropy, it must utilize category theory. Even two categories must be used. And although in the previous theorem, people were interested only in finite sets, now Gromov is very interested in the big numbers low and asymptotic passage to continuous limit. Trying to understand what is happening during this asymptotic continuous limit, he suggests to use methods of non-standard analysis. Of course, he stresses the role of convexity and suggests that such kind of new mathematics could be applied in problems, mathematical problems arising in cellular biology and molecular biology. So, speaking about convexity as an important notion, let's come back to this idea of Stone to consider algebraic structure axiomatizing properties of convex combinations. So if we have T, a number between 0 and 1, and 2 points of an affine space, we can associate with these 2 points another point, which is the result of this convex combination. And this operation could be understood as an operation depending on the parameter t, which can be applied to two arguments x and y. As such, it looks like some kind of product, although it's related rather with to additive structure or affine structure. But anyway, it satisfies associativity, which means that if we have the distribution of brackets as on the left-hand side, we can move these brackets as you see on the right-hand side for the price of recalculating these parameters of convex combinations. From parameters st, you obtain some new parameters u and v, which I will show you in a minute what formulas could be used for this recalculation. Next, this operation is in a sense unital. Unitality here means that if the parameter is equal to 0 or 1, in fact, every element could serve as a unit. Commutativity means that if we reflect the unit interval 0, 1, then this is the recalculation allowing us to change the order of this mixing.
Sorry, so what is W? Is W 1 minus T?
Yes, it's a reflection.
Okay, thank you.
And there's an idempotency axiom which says that if we mix X with X with the same X, then irrespectively of this parameter T, we obtain X again. Okay. So these are these formulas of recalculation of some parameters to some other in these axioms. Okay. So when we have such an abstract operation on two arguments depending on a parameter T from an interval, unit interval 0, 1, then we say that this structure is called abstract convexity, and set equipped with such a family of operations is called abstract convex. And there are some abstract convex sets which cannot be embedded in an affine space. We can devise some examples when we are using some formulas depending on maximum or minimum functions, and they satisfy all these axioms, but they cannot be written as convex linear combinations of points in an affine space. So, as usual, if we have some algebraic structure, we could think about this algebraic structure as encoded by some monad. And if we have some monads, we can speak about bimodules over this structure. For instance, if you have the category of commutative rings, then the corresponding category of bimodules in this operatic sense, monadic sense, is a notion of a symmetric bimodule or one-sided module. If we think about associative algebras, then this operatic counterpart, this bimodule, operatic bimodule notion, is simply bimodule in the usual sense. So it's not a surprise that if we have this structure of this convex abstract combinations, this structure also must have its operatic counterpart, and this kind of counterpart is called absorbing symmetric bimodule. So I'm introducing this notion to use these bimodules as coefficients in some kind of Hochschild cohomology I'm going to construct. Okay, so you see that three first axioms correspond to associativity. Next one corresponds to unitality. Okay. Last but one corresponds to symmetry, and the last one corresponds to idempotency. So it's a linearized version of idempotency.
Sorry, Tomek, do you mean here actions on X or?
No. So X.
Ah, the abelian group which acts on the bimodule. Okay.
Yeah. So M is an abelian group which is acted on by our abstract convex set.
Okay, sorry. Yes, thank you. Mm-hmm.
Okay. So since it's a seminar on noncommutative geometry, very natural attempt would be to would be very natural to forget about everything which depends on commutativity, and we can do this. And then instead of speaking about convex sets, we could speak about mixed sets. Okay, and they have their own bimodules, which are these bimodules in the previous sense, but with the when we forget about symmetry of this mixing and symmetry of this bimodule. Then we obtain more general theory. This is very minor remark, but in some physical chemistry, people consider mixing of substances when the result of this mixture depends on the order of this mixing. And this is very interesting because some models of mathematical models of molecular biology or even cellular biology of theory of cells requires to explain what is the origin for something which are called micelles. And these micelles are fundamental structures in biology. Among them, we have cells, a boundary of living cells, and they correspond to processes that could be produced by processes which are non-commutative. So this opens some very interesting prospect on some non-commutative biology, in the sense that this theory of these mixed cells could be used as a formalism to describe basic mathematical models of cells, living cells. Okay, so among these bimodules, we have bimodules which I call trivial, and it's very nice exercise, very simple calculation, that if we have an arbitrary vector space V, and we define an action of an abstract convex set by the following formulas. For the left action of X is simply multiplying by this T, and right action is multiplying by 1 minus T. All these actions are fulfilled. Okay, so such bimodules will be called trivial. Okay, so having these coefficients, we can start constructing our Hochschild cohomology with coefficients in these bimodules. So it's a play. It's a quite complicated play between this mixing of two arguments and mixing of many arguments. Okay? And mathematics of this comparison between iterated mixing of many arguments, x0, x1, up to xn, with single mixing, with a single parameter, maybe not single parameter, with a parameter in the space of probability distributions, delta m. Mathematics of this comparison is encoded by a birational regular method, given in the following way. If we know these single parameters T1 up to Tn, we can recalculate corresponding weights of this mixing of many arguments. Okay, so in one direction, we have polynomial formulas expressing PIs in terms of these parameters T, but we have also inverse formulas which are rational, expressing TIs by these weights of this mixing of many arguments. Okay? You can easily guess what should be these formulas if you think about this. What should hold in an affine space?
Tomek, when I look at these deltas, are these simplices? So delta 1 is just...
Yes, delta 1 is a unit interval.
Okay, and that's an n simplex.
Yes, and delta n is an n simplex. So then we can form the following complex, whose cochains are maps from the Cartesian product of the n-dimensional simplex cross nth Cartesian power of x. Maybe the Cartesian power sign is missing here. This is x raised to the nth Cartesian power. Okay, taking values in n, and then I'm using the notation map because I don't want to restrict myself to a fixed class of functions, but by map I will usually mean maps which are sufficiently regular, at least measurable, but mostly it's continuous. Okay, and then we can construct the co-boundary operator. It should be familiar if you remember the structure of the differential, the co-boundary operator of the Hochschild complex. However, we have many recalculations which are necessary to devise this co-boundary operator satisfying. First of all, which is well defined, and second is satisfying this identity d squared equals 0. Okay, so these are these formulas necessary for adjustment of these weights, of these parameters of these mixings formula. And you again see that some of them are very simple polynomial, but some other are rational maps. Okay. So we have the following lemma. If we restrict ourselves to barycentric coordinates in a simplex, on a simplex, where the last coordinate is equal to 0, okay, then we can think about restriction of this chains of this complex to simplices of smaller dimension, because every simplex can be understood as a cone over the opposite side, which is a simplex of dimension n-1. Okay, and then it turns out that if we have cochains which restricted to such smaller simplex, to some phase, vanish, then their co-boundary also must vanish, which means that we obtain some complex. We can take the quotient complex, dividing by such cochains defined in this lemma, and we obtain something which we call reduced complex, which is denoted by C bar. Okay, so the difference between the initial complex and this one is that the dimension of the simplex here is smaller by 1. Okay. So now I'm going to show.
Sorry, Tomek.
Yes?
So this is like dividing by 1 in the usual Hochschild homology of unital algebra.
Dividing by 1.
Yeah, you have these A bars in Quillen's papers, you know, but you kill V1.
I don't know.
You do have reduced Hochschild complexes for algebras.
Yes, yes, I know this. Therefore, I'm using this terminology, but it's more radical here, because if you think about the 0th part of this complex, it would contain the simplex of dimension -1, which is an empty space. It's an empty set. Okay, and functions on an empty set are 0. So this construction does more to this previous initial Hochschild complex than this reducing in the classical Hochschild complex. it kills these zeros chains. Okay.
Okay. Thanks.
Okay. So if you remember, the reason for inventing this Hochschild cohomology was the theorem of something which is called Hochschild extension. It's an extension by square zero ideal. Okay. So now I'm going to show you that in this context of abstract convexity, you can also speak about analogous kinds of extensions. So for this, we have to have some action of a trivial bimodule V, okay, on why trivial? No. This could be arbitrary M. I don't know why I put trivial here. So E is an abstract convex set, which is my extension, which is acted on by some bimodule, let's say V or M. Okay? This means that E is acted on by V by the following form, satisfying the following rule. It's some distributivity of this action with respect of this mixing with respect to this action.
Sorry, Tomek, but I keep on being confused. Who acts on whom? Convex sets acts on a bimodule, or bimodule acts on a complex convex?
No. Bimodules are always acted on by abstract convex sets.
But you wrote it differently. An abstract convex set acted on. So here you wrote it the other way around.
Yeah. E is an abstract convex set.
Yes. And you act on the abstract convex set by trivial by module.
Sorry, thank you for yeah, it's a typo, of course.
Okay. So I have two typos in here.
Yeah, acting on maybe more.
Exactly.
Maybe more. Acting on freely by yeah, something strange happened here.
I mean, freely acting.
Yeah, it's a result of copy and paste. Yeah.
So you really want freely acting on an arbitrary bimodule V. Okay.
And this compatibility of this action and this mixing is the distribution of this mixing over this action. Okay.
And what is free action? What is free action? What does it mean here? Of a convex set.
So this trivial bimodule is an abelian group.
Non-trivial, any bimodule you said.
Any bimodule is an abelian group.
Okay.
So this group is acting freely.
Okay. Really action on a set which is convex. Okay.
Yes. So you can think about this action as a kind of cylindric set with an action along the generators of the cylinder. Okay.
Tomek, may I ask a question?
Yes, please.
What does it mean that there is an this action between V0 and V1? So
No. It's a mixing of V0 and V1. So sorry. Now I understand why I put here trivial bimodule. If M should also be a real vector space, not a abelian group. Okay. So every vector space is an abstract convex set.
okay, so this trivial mixing is this multiplying by T or 1 minus T, right?
No, it is the standard mixing coming from the structure of a vector space as an affine space.
Okay.
So we don't have action of a module on a module, bimodule on the bimodule. We have only action of the bimodule on an abstract convex set.
So it's just a barycentric combination of V0 and V1.
Yes, convex.
Or convex, yeah.
Tomek, sorry, I'm getting completely confused. What acts on what?
Abstract convex set
So E acts on V.
a bimodule V.
On bimodule. So what is V circle V?
So this bimodule is a vector space. It's
So by itself is an abstract convex set.
It's an abstract convex set. It's a convex combination with parameter.
So it's an abstract convex. So you think of VE acting on a abstract convex on the canonical convex set structure V.
Yeah. So V is yes.
Thank you. Okay.
So we have two. If you think about the cylinder I described a minute ago.
What are V orbits? Sorry, next line. What are V orbits in E? It's E that acts on V, not the other way.
E is acted on by V.
No, you said that E acts on V. Again, once again, what acts on what?
No. V acts on E. Sorry, this was a typo. Piotr spotted. Okay, here. Sorry for this confusion.
No. So sorry. So this says that
E is acted on by V.
The
vector space.
Single sentence. V acts on V or E acts on V. What acts on what? Letters.
V acts on E.
Thank you.
And freely.
So then there's no typo.
So there is no typo. V acts on E.
That's what I asked you. So you are completely confusing.
Oh, so maybe I was reading this. When you asked me this question, I was focused on this trivial bimodule. I was so busy with trying to understand why I put.
So what is bimodule here? Why these bimodule? Sorry. These bimodule under what?
It is acted on. It's a bimodule over E. So we have
no, but E does not act on V. V acts on E.
No.
What acts on what?
Okay. V is a bimodule over E. So you can speak about axes, left and right axes, but one.
No, you can't. So sorry, V is bimodule over E.
V is a bimodule over E.
And it also acts on E.
But being a vector space, it also acts freely on E.
Mm-hmm.
Okay.
Why?
It's a definition.
It's not a convex set. So why V acting on E makes it bimodule over E?
No. So V is a bimodule over E.
Yeah.
Okay.
So E dot V is left or right is in V, right?
Mm-hmm.
So E dot V is in V, right?
Oh,
No.
is it
Except
true
for V is
that,
in V.
No.
sorry,
This
actually
mixing on the left-hand side is
I
a
don't
mixing
care which side.
on the left-hand side of this identity.
I don't care which side. It's a bimodule over E. So E circle V is in V, right? Or what?
I mean, are you trying to say that there are two independent structures, that this action of V on E has nothing to do with a bimodule structure?
in fact,
exactly,
there
that
are
was
four
my impression as well.
Okay, so I realized that, okay, there are four structures, okay? So V is a bimodule over E,
Okay.
okay? Next, E is a module over V. This action is denoted by plus,
Okay.
okay? There is a mixing in this abstract convex set, which is here.
Mhm.
No, it's in V. It's not in the abstract convex set. E
This
plus V.
mixing
No,
is in the
Thomas,
E.
you just said E plus V is in V.
No, not in
No,
V.
in
It's
E. In E.
So E
It is
plus
an
V is
action
in
of
E.
V on E. It's like you have a
This
point
is
and you have a vector,
Tomek,
and you are
it's
moving
like
this point.
is this
Yeah.
like an
It's in E.
action of
Yes,
a
yes,
vector
yes.
space on an affine space? That's what you.
Precisely, yes. So I started to explain it.
That's what they're trying to say.
You
Okay.
have a point of in a fine space, and you have a vector. and you are
Okay, fine.
moving this point via vector, obtaining
You get
another
another
point.
point in a fine space. Good. Okay.
So therefore, I tried to explain this on this example of a cylinder. Okay,
Wait. So now
the direction of generators of the cylinder is like a fine space of type V, and perpendicularly it is like E. Sorry, it's like this quotient. It's like this X. Okay, so the base of the cylinder is X, is the quotient of this E modulo the action of V, and this is the set of V orbits in E.
Okay.
Okay, so we have a canonical projection from this set to this quotient, and this satisfies the following universal property. Okay, so this is the structure of the situation. Okay, and this is universal with respect to all these maps from E to some other convex sets Y, which are acted on trivially by this V. Okay, and then if we take the set theoretical section of this quotient map, then we can rewrite the cylinder as a product. It will be like X cross V. However, this action of V and the action of and this mixing in this abstract convex set E, they are twisted by this set theoretical section of this projection. And then this mixing in terms of this pair XV can be written in the following way, with some correction. Ct, which is a function depending on t, and these two arguments x0 and x1. Okay, so obtain some function c, and associativity of this mixing is tantamount to the two cocycle condition, which I wrote here. Okay, so this two cocycle condition in our reduced Hochschild complex. And exactly as in the classical theory of Hochschild extensions, we can prove that cohomologous cocycles define isomorphic extensions. So the second cohomology of this reduced Hochschild complex classifies extensions in this sense. Okay. This is not the only thing which, the only complex which we can construct in this situation, and not only kind of extensions. Among these extensions, we could distinguish a class of so-called crystalline extensions, which are defined as follows. They are described by cocycles, which are cohomologous to cocycles having special property. This property is following. First, we choose a maximal set P of a finely independent external elements in this convex set. You can think about this abstractly or concretely in the case of subsets of convex subsets of an affine space. It doesn't matter. And we call such extension crystalline if this cocycle satisfies this condition that fixing the maximal set P of a finely independent external elements, there exists a function which depends on a parameter of the mixing only, and the choice of this maximal set of a finely independent external elements. So it's a function from the unit interval to V. And satisfies this condition that whenever we have arguments xi belonging to convex halves of parts of any partition of this set of finally independent external elements, then the value of this cocycle on the pair x0, x1 is independent of the choice of x0, x1 in this convex hull of Pi. Okay? So this means that you can move x0 and x1 in the hull of this convex hull of this Pi, but the value of this cocycle doesn't change.
Sorry, Tomek, but I have problems with reading your English. For me, this doesn't make sense grammatically. I mean, which for every maximal set there exists a function, I don't understand it.
So this is a condition. Okay.
Yeah,
so
but I understand what you're saying. For me, it doesn't make sense
problem. Yeah.
in English.
Okay. So these are such cocycles when you can move this x0 and x1 freely, but inside of convex halves of some partitions okay, of a finally independent external element, a set of elements.
So can you correct it so that I can read it?
Now,
Yeah.
maybe after.
No, but okay. So what should it be? Just don't explain the math. Just give me the syntax.
Cocycle is called crystalline
Yes.
if for every maximal set P of a finally independent external elements.
So here's if, not which.
Yeah, but
I'm
create a
confused.
new
Your sentence is
sentence.
for me incomprehensible. I cannot see the logic of what you're saying.
We call an extension of a
Yes,
convex
that's
set by
fine.
vector space V crystalline.
Yes. And now you have a condition. If it's cocycle, I'm not a cocycle, and now I'm lost.
Homologous to a cocycle.
Yes, fine.
And now, which for
Yeah.
every maximal set P of a finally independent external elements.
And something is missing. There exists a
Yeah.
Instead of which should be
Such
and.
that. Sorry. So the syntax should be such that instead of the switch. Okay.
Okay. Okay, thank you.
Thank you for the correction. Okay.
Okay, wait a minute, but this basically tells you that it's pick up your find set, sorry, pick up your set of external elements.
Yes.
And then you are saying that cocycle depends only on this set and not the points, essentially. Because for any points with two different points, you can partition your set into two pieces such that these 2 points are convex combination.
Yeah. So this cocycle is, so if you think about this
It does not depend really on the
chambers, then this cocycle, the values of this cocycle depends only on these chambers.
Only on what?
Convex halves of these parts of this partition.
Yeah.
Okay.
No, because you change partition, right? You can change partition.
No. This must be for any partition.
Yeah, but so
provided
you start with Thomas, you start with a set P, right? And now each time
but this condition is for every set P. Yeah.
You fix your set P.
Okay, I'm starting with P. Then I have
and now you're saying do any partition.
Yes.
And then values of cocycle for the points in the two different convex halves of the two parts of this partition does not depend on the points.
Yes, depends only on this partition, on convex halves of this partition.
That's not what it says.
Why?
It says it depends on your choice of a set P.
No.
That's
For
what you
every
know.
maximal set P, this condition is fulfilled. So if I change P, capital P,
But it does not depend on the
I'm
partition of
changing
P.
this function CTP.
It does not depend on the partition of P.
No. But the value of C depends only on this partition, provided
That's not what
xi,
you wrote. That's not what you wrote.
such that for xi in the convex hull of Pi, Ct x0 x1 is equal to CTP.
CTP, that depends on P, not on the partition of P. You wrote it does not depend on the partition.
Yes, so the condition on x0 and x1 is that they are in convex hull of some partition of P.
Yeah.
Okay. The condition on the function C blank P is that this depends on P.
Yeah.
So the function C blank P is common to all partitions, but it depends on the choice of the maximal set P.
You pick up your maximal, you pick up your, I don't know, you pick your external points in your complex set, right?
Yes.
Suppose you have finitely many external points. Pick up these points, right?
Yeah. Then.
Fine. When you are saying that, well, no. When you are saying that there is a number, sorry, that there is a function
Depending on this P,
we fix P, right?
that for every partition of this
There are
P,
no other choices of P. If you have this, say, nice convex set, they take external points of this convex set.
No. I can have many choices of P. If it's not a simplex, you can have many such.
I suppose it's a simplex. I think
Yeah, of course, if it's a simplex, then there's only one choice. There's one maximum.
No, TOMASZ, question is not the choice. You chose your P.
Yes.
Right?
Yes.
Once you chose your P, then value of C does not depend on how you partition your P. That's what it says.
But no. But I'm testing my equality on x0 and x1, which belongs to the convex halves of these parts of this partition. And this must hold for all partitions.
Yeah, you get the same number for partitions, right?
Yes. Because this number depends only on the choice of P.
So that's what I'm saying. So the C is almost independent of points x0, x1.
Not exactly, because this equality holds on only provided this x0 and x1 are in disjoint parts of some partition.
Of a fixed set, right?
Of a fixed set P, yes.
So C is basically uniquely okay, there's not much space for you.
If you couldn't how to say, if you couldn't separate this x0 and x1 by such a partition, you do not expect that this equality would hold.
But the values are values are.
I'm not saying about such evaluations on such.
Okay, you are saying that for any 2 points that you can separate, the value is the same.
Yes.
Independent of separation.
Yes. So this is a generalization of a condition you saw today. It was maybe I should come back for a while. Where is this? Yes. Can you see this equation number 3?
So
in the point number 3. Can you see this?
Yeah, sure.
So think about P1, P2, Pn as some convex combination of. So this could be regarded to be a convex combination of points in a simplex.
Yeah.
Okay, and look, if you think about this difference between the left-hand side and the first summand of the right-hand side, you obtain P1, which is independent of the choice of Pi's. Can you see this? It's P1 times I, and depending on T, 1 minus T. So this function 1 minus this function I is applied now to only these coefficients, these parameters T and 1 minus T, only these two weights. Can you see this?
Yeah, sure.
So my condition is a generalization of this, but it makes sense not only for simplices, but it makes sense for arbitrary, let's say, polyhedra, polytopes. But of course, if X is a simplex, you have only one maximal finally independent external set, which is a set of vertices of the simplex. Okay, and then the partition of this is like taking two faces of the simplex, which are spanned by different subsets of vertices. Okay. Is it clear?
Yeah, okay. So you're just saying that the value on the faces is in the constant, essentially constant.
Yeah. So on the simplex, if I'm taking the convex combination of 2 points, yeah. Yes, please.
No, wait a minute. So any 2 points. No, you are not saying anything about value for the points in the interior. You're just saying something about value on the faces. Yeah.
But the whole simplex is also a face.
In what? In itself? No. You are not saying
yes, in itself. But then I don't have this.
You don't. No. You don't have partition. No. You're just not saying anything about the interior, right?
Yes, for the simplex is yes. Because it would be 0. This cocycle would be 0 if
what? Why? If what? Sorry. You're just not saying anything about the points in the interior.
Yeah, but I'm talking about two points here.
Yeah, sure.
Because I'm talking about the 2 cocycles.
Anytime, if any of these points is in the interior, you are not saying anything.
No, anything.
Precisely. Okay.
Yeah. Okay. So this is this dependence only on these chambers.
Why crystalline?
Yeah, it explains why I called it crystalline. Okay. You can extend this notion of this cocycle defining crystalline extension to some higher cocycles. Sure. So the general definition is like this. Then if we have another typo. This C would be overlined. Okay, this is it's a cochain in this reduced complex. Okay.
Like this?
Yes. Thank you very much.
Tomek, by the way, you have 10 minutes left.
Okay. So this is called crystalline. If for every maximal set, again, it's a repetition of this previous condition. But now, instead of having a partition into two subsets, we have a partition into n+1 subsets. And the condition is like this. So instead of t, an argument going through the unit interval, I have an point of a n-1 dimensional simplex, which is called p. Okay, but again, this cocycle is like this, or even a cochain is crystalline if it satisfies this condition, analogous condition. It depends only on the choice of this p. Equality is tested for x0, xn, which are separated by convex halves of parts of this partition. Okay. What is interesting?
What is this p doing there?
Small p.
Yeah.
It's a point of an n-1 dimensional simplex.
And
oh, sorry. Again, typo. Yeah. It shouldn't be I. It should be delta n-1. Another result of copy and paste. Sorry for that. But I read it as it should be. Okay. So why this condition could be complicated, but what is nice about it? The next lemma says that the crystalline cochains form a subcomplex in this reduced complex. Okay. Although it was quite complicated, it was such that it's easy to check that it is a subcomplex, closed under D. Okay. And then we can form also the quotient. And we call this quotient entropic. Okay. So in a sense, I'm dividing this complex into two parts. I have this crystalline subcomplex, and I have this quotient, which I call entropic. Okay. So these are two, let's say, opposite phenomena, which are separated by this. And then there's a theorem. Provided X has at least 3 extremal elements. So, for instance, for simplices, the simplex must have dimension at least 2. Okay. This function determining this crystalline extension of X by V satisfies the fundamental equation of information theory.
I should be delta n.
Oh, sorry,
Capital N.
again, you are right. No, it should be delta n-1. Thank you very much. The same pasting. Okay. So this says that fundamental equation of information theory, in fact, comes from homological algebra related to abstract convex structure. Second theorem says that, okay, so now let X be a simplex, and V will be a trivial one-dimensional bimodule over X. Okay? Then the first cohomology of the entropic complex is generated by the class of the Shannon entropy, modulo functions which are polynomials of degree 1 in barycentric coordinates. Probably barycentric has some typo, but forgive me. Okay. So this means what is Shannon entropy? It's a generator of the first cohomology of this entropic complex. Okay. So
what X on what here? Oh, how?
Sorry.
How does V act on X?
No. X is this quotient. When I was talking about extension.
Oh, yeah, that's extension. Okay, yeah.
X, yeah.
I'm talking about extensions here.
So E was let's kind of a square zero extension by V by R, in fact, of a simplex now. Okay. Then the Shannon entropy is the generator modulo function polynomials of degree 1.
Sorry, Tomasz, why do you say that X is the simplex? So which one is
Yes.
it?
Any simplex. Okay, a simplex.
I see.
A simplex. Okay. Yeah, but yeah. Dimension, except the dimension must be at least 2. Any all simplices look alike. Okay, so but there is another part of this theorem, that if we have this subcomplex, complex, and the quotient complex, we have a connecting homomorphism in the long exact sequence of cohomology groups. And this connecting homomorphism maps this Shannon generator onto a generator of the second cohomology of the crystalline complex, representing a crystalline extension described by the solution of the fundamental equation of the information theory. Okay, so this relates this fundamental equation of the information theory with entropy by this connecting homomorphism in the long exact sequence.
Okay, just to make sure that we talk about the same things. So X, so essentially X is a simplex. And when you look at cohomology of X with values in V.
In R.
In R, right? Okay.
Yes.
So, so the boundary, so what quotients are you talking about? So what
I'm taking this reduced
what boundary map are we talking about? In what? In which complex?
So I have this
in the short exact sequence of complexes. What complexes?
Yeah. Crystalline subcomplex, reduced complex, and the quotient is this entropic by definition.
Okay.
Okay.
Fine.
So this fundamental equation of the information theory sits in something of crystalline nature. Okay. But Shannon entropy lives in something of entropic nature. Okay. So there's an analogy of this construction in complex geometry. If you have, for instance, the sheaf of invertible functions, okay, then you have the exponential short exact sequence whose kernel consists of integers. Okay, then we have additive functions, and then you have these invertible functions. Okay, which is the image of this exponential map. In such a situation, H1 with taking values in these invertible things, it is like line bundle. Okay, but if you have the first term class of this line bundle, you obtain an element in integral cohomology of a space. Okay, so this connecting homomorphism is an analog of the first term class. So in a sense, this first term class is the solution of the fundamental equation of the information theory. This is of crystalline nature, but this line bundle kind of thing is the Shannon entropy. Okay, so this analogy with classical very well known connecting homomorphism, okay, relating to natures of opposite, two types of opposite nature. So this crystalline corresponds to discrete, like integers, okay, and this entropic is like being like functional, like line bounded. Okay, so final remarks. So you see that the origin of this is quite different, of this equation, fundamental equation of information theory entropy is completely different comparing with this case theoretical motivation. However, this dissection into partitions in the crystalline property, it resembles somehow this philosophy of scissors dissection, okay? Because in both things, we are dissecting something into some pieces, okay? Moreover, this makes sense also for higher cocycles in our Hochschild type cohomology. Similarly, if the classical theory of
sorry, Tomek, I'm sorry,
yeah.
but I'm again confused by what you write. What does it mean, dissection into partitions in the crystalline property?
Crystalline property was defined by the property of some cocycle.
Yes.
And this cocycle was tested, this property of this cocycle was tested on some partitions of maximal finally independent subsets of vertices. So you are partitioning this P into some P0, P1, P2, and so on.
So what are you partitioning?
The maximal affine independent set of external points.
Okay.
Okay.
Because I'm confused by the grammar. Is it in or off? I mean, you are doing partition not of a property, but for me, it's difficult to understand that you are partitioning something in property. It's very weird.
In the crystalline property, there were partitions. Okay, and we're dissecting some points, external points into.
So what you mean is that dissections into partitions that you invoke when defining crystalline property.
Yes, defining crystalline property. Yeah.
Okay. So that's, I don't know, that's a bit.
It was some part of this quite long definition of crystalline property.
Yeah.
But partitions were there.
Okay, yeah, and I've got it, but I think you could say it much more clearly.
Okay. Thank you for the correction. Okay, so we have completely, apparently independent ideas of dissecting something, but at the end of the day, we obtain the same result. So maybe this story is not about one or another situation when this entropy and this fundamental equation of the information theory arise, but maybe it's about some abstract partitions even. I don't know. The second remark is that this entropy was related to this dilogarithm function or infinitesimal version of the dilogarithm function. But higher polylogarithms also are related with convex geometry because they are integrals of very standard simple rational differential forms over simplices, the result of our model. Okay, so this convex geometry somehow is hidden in the definition of polylogarithms as a structure of a domain over which some standard differential forms are integrated. Okay. So very long shot, but maybe some very maybe premature, but some question makes sense. Okay. Are higher crystalline cocycles, okay, relevant to algebraic K-theory of fields? In particular, are they related with polylogarithms? Okay. If the story is that independently of particular realization, it's a tip of an iceberg of some results about very, very abstract theory of partitions, maybe there is a common root. So this question is the end of my talk.
Thank you very much, Tomek. I understand that as a reward for answering the question, there is a banana. Okay, thank you so much.
Remember to give it to him.
All right, so time for further questions. I mean, there's only one question asked by a gorilla. Maybe there are some more. Anybody? Richard asked already many questions, but you are more than welcome to continue.
It's okay.
Ludwig, Tomek.
Well, I have very stupid, simple. What is a twisted real line, Tomek? Sorry for that stupid question, but please tell me.
It was a real line twisted by some power of square root of -1, okay, depending on parity of this exponent. And at first, I wanted to eliminate this, simply writing I to some power. But then I realized that authors were using natural identification of this real line with some standard orientation. So raising I to some power, because powers of I are periodic, but with period 4, would be some powers of -1, changing this natural orientation. So some formulas would be not so transparent.
Okay, thanks.
Actually, it should be 1 over 2 pi I to the power n.
Probably.
So there's also this 2 pi to the power n involved.
Probably, yes. And in then invariant, when you are speaking about angles, you are counting them modulo 2 pi. But if you are creating an invariant in K-theory, you are dividing by 2 pi to obtain numbers modulo 1.
Yeah, sure.
Yeah. So maybe this appearance of these twists definitely should take into account this phenomena. Divided by 2 pi.
Called Tate twist. So
Tate twist. Thank you very much. Yeah, it's a Tate twist.
All right, anybody else? Andrzej? Nope.
No question.
All right, if there are no further questions, then let us thank Tomek again. Thank you so much. I'll stop recording, but please don't go away.